Hello kids, today we're going to be discussing Unit 3 for Grade 7 Science for Cambridge. Unit 3 is Force and Motion. So in this chapter we are going to be discussing how forces can generate motion. Then we're going to relate force and motion, how different types of forces can generate different type of motions. Then we're going to get into the idea of describing motion in terms of graphical data, or to be able to understand the graphical data and describe the motion, right? And then we're going to understand how forces, linear forces or forces in one line, can cause rotational effects or the turning effect we call torque or moment, right? Then we're going to see how forces can be translated into pressure of solids, liquids and gases. And finally, we're going to understand how particles inside the matter are on the move, and how the forces inside any matter, the atoms and the particles, how forces are interacting at that level, right? So let's get into the first subtopic, which is balanced and unbalanced forces. So let's discuss balanced and unbalanced forces. But before that, let's get into the idea, what is force, right? What is force? So force is the ability to do some action, right? Or to do some work, right? Work, motion, action, right? So it can be expressed in several ways, but this is how I basically describe force, right? So force is the ability to do some work. For example, if there's a box, right? I apply some force on the box, so the box is going to, move from here to here, right? So the box is going to be moved here, right? So as I said, that force is the ability to do some work, right? We did some work, we moved this box from here to here, right? So this is also motion, right, or an action. So it can be expressed in all either of these three terms. Now for this unit, we're only going to be concerned with motion, right? How motion is generated depending on the forces. So for any object to move, or to have some work done on it, we need to understand it needs to cover some distance, right? So whenever we are covering some distance, we say that we're in motion, we are moving, right? When we move, we cover some distance. So we need to understand that how forces generate motion. For this, we need to understand two ideas about force, that there are balanced forces and then there are unbalanced forces, right? So in this image, you can see very well over here that these are balanced forces, right? Let me just zoom it out a little bit, right, from the page. uh, so that we're much more better. Yeah, okay. Now if you look at this, we have balanced forces, right? And when we talk about balanced forces, we understand that these are the forces which are equal, right? So I'm going to tabulate this in a moment. So as you can see, there forces on the left and the forces on the right, and the value for each force is 20 newtons, right? So over here I'm going to discuss that it is newtons, right? It was a scientist Newton who described force, right? So the unit of this force is described in newtons, right? Represented by capital N. So how much force is applied when we quantify, when we try to express force in numbers, we use this letter capital N for the unit, right? So this is the unit, right? Okay. So when we have these two forces on the right and on the left, as you can see, they are equal, right? So we have equal forces. When we have equal forces, this is a case for balanced force, right? So we call these as balanced forces. They are only balanced when they're opposite, right? Now imagine if there's a box, right? There's a box. There's one force which is 10 newtons, and there's another force in the same direction, right? Let's say that's also 10 newtons. So what is going to be the net force? Net force means the sum of forces. Now as you can see, both forces are in the same direction, so they'll end up adding up together. So that would be 20 Newton of the force, right? So we need to understand that for forces to be balanced, now this is not a balanced force. Why this is not a balanced force? Because both the forces are in the same direction, right there or towards the right. But if you look at this picture, we have forces acting on the left and forces acting on the right. So they are opposite to each other. That's point number one, and they are equal to each other. That's the only way they will, balance each other. And when the forces are balanced, then we are going to discuss the motion. As I said, we will be understanding how balanced and unbalanced forces are going to cause motion. We'll discuss in the next subtopic. So we'll understand how this balanced force is not able to generate any motion or disturb an ongoing motion, right? So we'll get into that in a moment, right? But for now, let's just look at unbalanced forces, right? So unbalanced forces are forces which are not equal, right? But they're still opposite to each other, right? Again, if they're not opposite, then we cannot discuss about balance. Why? Because they will add up and generate a bigger force, so which is already kind of an unbalanced force. But when we're talking about two forces which are opposite to each other and then they are not equal to one another, we call that as unbalanced force, right? And these forces are able to generate motion, right, in the objects. As you can see over here, there's no force on the back, right, or towards the left, so the object must go faster because the forces are adding up together. So this is also a case of unbalanced force, right? So before we move any further, I would like to first, give some names to type, forces. So forces which help you lift up or fly, they are called lift, right? And the forces which weigh us down, we call those as weight. The force which makes us move forward, right, we call that as thrust. And the forces which prevent our forward motion, like air friction, right, road friction, we call those as drag, right? So lift is the upward force, right? As you can see, the arrow is up. Thrust is forward. Weight is downward. This is due to the mass. The greater the mass, the greater the weight, right? And drag is due to friction. So greater the area, the more the drag. Lesser the area, less the drag. Over here, I'm going to signify example of a train, right? If the train is supposed to have a blunt end, right? Train front, right? If this is the train front, as you can see, there is more air it can take compared to the bullet trains, right? So that's why bullet trains are made a little pointy, so that air friction or air drag, right? This is drag. This is also drag. So drag is reduced using, pointy face. So we can say this pointy front of bullet train. So hence bullet trains can go faster compared to the trains which are in Pakistan. We are still living probably 30 years back in the years, compared to rest of the world. So we still haven't understood the idea that having a pointier face on the train is actually going to help the train go faster and consume less energy. But we're still stuck on the flat front trains, while the rest of the world is now using bullet trains to reduce this air drag, right? So this is air drag which is slowing the train down. And for lift, definitely we need to generate more force that is going to pull us up, right? We can see that the birds actually flip their wings to push the air down, while the bird itself goes up, right? Please don't mind my drawing on the bird. Uh, Now for thrust, these engines, right, of the aircraft are going to generate forward thrust. They take in air, they burn the fuel, and they try to push that air out at the back, right? And that makes the whole plane move forward, right? Since the burning gases are pushed out of the engine, so as a reaction, the aircraft is going to be pushed forward, right? So that is very common. I always give this example of thrust. Let's say you are on a boat, right? You don't have any, it's a rowboat, right? And you don't have any rows to, go about it. So how are you supposed to move forward, right? You want the boat to move forward in water, but you don't have any rows, right? You don't have any paddles for it. But let's say you have some, mass over there. So what you're going to do, you're going to simply throw the mass out, right, from the back. As a reaction, the boat is going to move forward, right? So once you push this extra mass out of the boat from the back, as a reaction, the boat is going to move forward. So Newton said this: to every action, there is equal and opposite reaction, right? And please don't mind my writing because that's the writing tablet. It's very slippery, so I'm unable to control still after 1 year. It's still the same. Okay, I was hoping it would get a little rough and get a little more dragged out. Okay, so that's the idea how the forces are balanced, right? As we go faster, the drag is going to increase. And why is going to increase? Because we just discussed this, that to every action there's an equal and opposite reaction. And when we talk about action, we're talking about force, right? And that's what Newton's third law of motion, or the Newton's law of force, describes force, right? So for weight we have lift, or for lift we have weight, right? When you try to go up, the weight is going to pull us down, right? If we try to go forward, the air friction is going to slow us down. So for every action there's an equal and opposite reaction, right? So this is just a basic idea of how different forces interact, right? Now let's get into the calculative part. Now in this case we're going to identify if these forces are balanced or unbalanced, right? And resultant force is the sum of the force. Now remember, if the force is on the right, when they're opposite to one another, we subtract. When in the same direction, we add, right? So let's give this a little idea. Same direction adds force, opposite direction subtracts force, right? So for this tiny little principle, we're going to solve this little question here. Now over here you can see on the left there is 500 newtons, and on the right there is 750 newtons. So I'm just going to erase this board thing from here, right, to have some more work area, right? So as well as this bird, right? Now this is going to be 750, right? I'm always going to deduct the bigger number from the smaller one, so it is going to be 750 minus 500. That gives you 250. So the resultant force is 250 newtons, right? Is it balanced? It's unbalanced, right? I'm just going to write UN, unbalanced, right? Okay, direction of the force, that is towards the right, because this force is greater, right? Okay, in the second case, when we're talking about this one, as you can see, on the left there is 400 newtons, and on the right there is 400 newtons, right? So they appear to be equal. So equal forces are balanced forces. So I'm just going to write B. The resultant force, 400 minus 400, is going to be 0. So it's 0 newtons, right? Please don't forget to put this N. Whenever you quantify any numbers in the subject of physics, you need to write the units, right? So Newton is right. And direction of the force, none, right? Why none? Because it won't be able to go to the right or the left, because forces are balanced, so the object is not going to move, right? Okay, now in this case you have 300 newtons versus 500 newtons, right? Again, I will take the bigger number, subtract the smaller one from it, so it is going to be 200, right? So the resultant is 200 newtons, right? And these are going to be, since there is net resultant force, so we're sure that this is unbalanced case, so I'm going to write UN. And over here, as you can see, the dominant force is towards the left, right? So we're going to simply write left over here, right? For the second last case, again, forces are equal. So 500 minus 500 gives you 0. So it's 0 Newton. It is not going to have any directions. That is going to be none. It is going to be a balanced force since they're equal to one another. So no motion is going to be there. In the last case, again, it is 1000 newtons minus 500 newtons, right? So the resultant force is going to be 500 newtons, right? And this is going to be an unbalanced case. And if you talk about the direction, then the direction of the force is going to be to the right, as this is the dominant force, right? So I hope I'm able to help you understand the basic idea how forces are going to interact. Now I'm going to move quickly into the second unit. Now please understand this, that I'm just trying to recover some of the basic ideas from the topic. I'm not covering the entire topic. So you're not supposed to base your assessments, assessment preparation on these topics. These are just to help you recover if you have any confusions left in the topic, right? So moving into the second unit, which is force and motion, we now understand, right, that unbalanced forces cause changes to rest or motion. Now, what is rest? Right? I've just stated these four definitions. Rest is the state of no motion. When the object is not moving, we say that the object is at rest. Right? And what is motion? When the state is changing distance over time. Right? When the state of the object, I missed the object. Right? Is changing distance over time. When an object covers some distance over some time, we call it as motion. Now there are two types of motion, right? A and B. Being constant motion, constant means equal intervals of distance in equal intervals of time. We are going to tabulate this, so no need to worry what this is all about. I will explain in a moment. And then we have a variable motion. When we have unequal intervals of distance covered in equal intervals of time, right? So we're going to understand these four basic ideas, right? So let's have a look at this diagram. As you can see, there are two people pulling the rope on one end, and there are also two people pulling on the other end. So these are balanced, right? And for balanced, we have no motion, right? They won't be able to move anywhere because the forces are equal, right, to the left and to the right. But in the second image, if you can see, there's still two people on the right, but there are three people on the left. So there's definitely more force, a bigger force over here and a smaller force here. Over here we had equal forces, right? Equal sides of the forces. So remember the arrowhead, the length of the arrow, right? This arrow, right? We call this as magnitude of force. How much force was exerted? It's represented by the length of arrow, right? Is represented by length of arrow, right? And over here, I'm going to use a different color, right? Arrowhead gives direction of force, right? So in which direction the force is applied. So keep this in mind, that this is how it works, right? So now let's look at this second case, in which you see a bicyclist, right? A cyclist is speeding up. As you can see, the forward arrow is bigger than the reverse arrow. Now over here I'm going to reinforce that this reverse arrow represents drag, right? And the drag could be the friction on the road as well as the air friction, right? So that those two things are representing this reverse arrow. But if the paddles are being if the cyclist is paddling fast, then he's speeding up. And if he stops paddling, then the front force is as much as the backward force as the drag. If he's just trying to keep its speed at the same, right, which we call as constant speed, right, equal intervals of distance and equal intervals of time. So this is going to be constant when the forward and the backward forces are equal, right? That's what I meant, that unbalanced forces can cause changes to rest and motion. So changes can be done to motion as well, right? Over here, the cyclist is at constant speed, but if the paddles are done faster, then motion can also be changed. And if the cyclist stops paddling, right, then the drag or the friction is going to slow him down. As you can see, only the reverse arrow is there and the forward is missing, right? So in this case, we're going to say that the cyclist is going to slow down. So this is variable, this is variable, this is constant, right? So this is variable motion, that when the forces are unequal or unbalanced, then the motion is being disturbed. So we call this as unbalanced, right? So what is equal intervals of time and what is constant motion, right? So let's compare constant motion and variable motion. So let me just tabulate this. We have distance, right, and we have time, right? So if I start walking, right, let's say I'm talking about myself, I cover I walk 5 meters, then I walked 10 meters, I continued walking 15 meters, I'm covering some distance, 20 meters, and then 25 meters, right? And every 2 seconds, uh, this is the value that I'm getting, right? I have a stopwatch in my hand and I'm checking my distance using a large tape, right, measuring tape. So I get to see that every time, for every 2 seconds, I'm covering how much distance? 5 meters, right? So this is the interval from one point to another. I'm consistently walking 5 meters every 2 seconds, right? So as you can see over here, the interval, right? Oh, sorry, my bad. I just, yeah, the time should also move forward, right? So it's 4 seconds, 6 seconds, 8 seconds, and 10 seconds, right? The clock is supposed to continue moving. So every interval there are 2 seconds, right? So for every 2 second difference, I'm moving 5 meters forward. So this is what I meant by equal intervals of distance, which is this 5 meter, right, which is equal interval. Interval is the difference of 2 points, right, in equal intervals of time, which is this 2 seconds at the bottom, right? 5 meters in every 2 seconds. So this is going to be constant motion, right? So let me call this as constant motion, right? So I will give this as arrow as equal intervals of time, right? And over here I'm going to tag this as equal intervals of distance, right? So this is going to be constant motion. Compared to this, let's make another case, right? I'm going to choose a different color this time around, right? So this is distance again, and we have time. I'm walking again, but this time my pace of walking is not the same, right? So I'm going to be clocking 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds, right? So for 10 seconds, I see how I walked, right? So in the first 2 seconds, I covered 5 meters. In the next, I covered, let's just say, 12 meters. I'm at 12 meters marker, right? And then I'm at 22, right? And then I'm at 34, and finally I'm at 48, right, meters. So as you can see, I'm running faster, right? Compared to the previous walk, I'm covering more distance in total amount of time. We'll cover how we can describe motion. So over here, the difference is 7 meters. Over here, the difference is 10 meters, right? Over here, the difference is 12 meters, and over here, the difference is 14 meters, right? But the interval of the time is 2 seconds, right? You're not supposed to draw these right on the top or the bottom of the tablet, but I'm just trying to help you understand that this is what interval means. So as you can see over here, we do have equal intervals of time, right? So remember this, that the time is always supposed to be taken in equal intervals. You cannot compare constant motion with variable motion if you are varying time as well, right? So you can only vary the distance. But over here, we can see unequal intervals of distance, right? I'm just going to write this. So as you can see over here, the distance is increasing every 2 seconds. So I'm speeding up over time, right? Initially, my speed was less, but in the next, I was able to cover 10 meters more, then I was going 12 meters more, and then 14 meters eventually, right? So this is going to be unequal. So we call this as variable motion, right? I hope I'm able to help you understand what constant motion is and what variable motion is, right? So this is where we're going to stop with the idea of what motion is, and now we're going to quantify motion. Now, all this time we discussed how much distance is covered and how much time, right? So I'm going to give you two ideas. First, we're going to discuss speed. So speed is how much distance an object or a person is going to cover in how much time, right? So we can say that if I've covered a distance of 45 meters, right, and I took time of 15 seconds, right? 15 seconds. So we can say over here, if you remember, I gave you some idea about this unit of distance and unit of time. Time is measured in seconds and distance is measured in meters in general calculations, right? Unless we're talking about very large distances or very small distances. In general, these are the standard units, right? What we call these as standard units, right? So I will come to the standard units in a moment, but first we're going to look at the formula of speed. So how much distance is covered in how much time? So we can calculate speed. I am going to represent it as v. There are several ways to give symbology to this, but I'm simply going to represent speed as v and distance as d and time as t, right? So over here, so speed is going to be 45 meters divided by 15 seconds, right? So this is going to be 3 meters per second, right? So what is the unit of speed? That is going to be meter per second. So now I'm at this point, I'm going to write the units, right? So distance is measured in meters, and we're talking about standard, right? Standard units, or the units which are adapted by rest of the world to calculate distance. That is in meters. As we know, there are 100-meter dash, 200-meter dash. When we talk about races, we're talking about meters, right? And then when we're talking about time, we're also looking at how many seconds it took for the diver to cover 100 meters or the runner to cover 100 meters, right? We cover time in seconds, right? So that is in seconds. As you do know that stopwatch also covers time in seconds, which we have experienced in the lab while we were trying to calculate speed of the object, right? And speed, since it is the ratio or the division of distance over time, it is going to be meter divided by second, right? So these are the units, right? So continuing forward, we have another idea. Now let's look at this idea. Now there is a person, right? I'm just going to make a sticky man. He's going to move a certain distance, right? This is distance, and we see that the stopwatch, right? The digital stopwatch with the buttons on it. The stopwatch is giving like 15 seconds, right? And the distance is 45 meters, right? So this is from point A to point B. So this is how we understand what speed is, how fast this person went from here to here is the speed, right? So the speed is distance divided by time. Now there are two ways to describe distance. This is what we call as generalized idea, constant speed. Over here, we are not discussing whether the person is going faster or slower in between. We just understand the fact that the person will be going at a constant speed. So this is constant speed, right? So I was scrolling for this reason. I just want to add constant over here. So constant speed is simply distance over time. But that's not necessarily the process, right? Maybe uh, a dog got after me. It started chasing me, so I must have started running faster somewhere, or maybe I stopped in between the path to pick up something, or to look at something. So we're not sure whether if the you know the traveling was constant or not. So we call that as average speed. So average speed is actually total distance over total time. When we are not sure whether the person was moving, let's say in a constant manner. Let's say it's about A and B, right? So I could have gone here, 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 round and round. So I took a certain amount of time. So the distance is the same. That is still the 45 meters. But I just, wiggled around, checking out flowers or something in the garden. So I covered 45 meter of distance from A to B, right? Distance is from A to B. But if I was not moving at a constant speed, or you can say I moved a little faster here, then I stopped, right, for a little moment, and then I started running faster. I'm going to put a double arrow, right? So this is going to be slow. Let's stop, and then during this distance, I stopped at this point and this point. I was still walking, so I stopped in between, and then I'm moving fast here, right? So I'm not sure if this is happening, right? This is what we call as variable, right? So the speed over here is changing, my motion is changing over here, but I forgot to tell you about that. I just told you that I covered 45 meters in let's just say 15 seconds again, right? This time around, I walked in a very unequal manner, right? So we're not sure. So we are going to call this as average speed. So when we don't know about the clarity, whether it's constant motion or purely a variable motion, if we do not have the values for variable motion, we're simply just going to work out average speed. That what is the total distance, because I stopped here, so it was part 1, right? Then this was part 2 between these two stops, and then this was part 3, right? So instead of calculating the speeds individually for each part, I don't have the values for it. I'm just going to calculate the average speed across the distance, right? Let's just say you're traveling from Islamabad to Peshawar, so you may not be traveling at the same speed. At times, the road may be a little higher, or it may be a little bumpy. So you might get a little slow going up, but you will experience some increase in speed while getting down, and then you will definitely be using brakes to manage your distance, and finally again you're going to increase your forward force to get over this climb. So the motion from A to B may not be smooth, right? Unlike a flat road, right? We don't usually have flat roads anywhere. We do have landscape changes. So because of that, the motion may not be constant, and that if we are only given the total distance, so this I will call as total distance, because I need individual distances to calculate these individual speeds, right? I don't have that, so I just have total distance and total time, right? So this is what we call as average speed, right? So it works out the same way. We have done some of the questions in the workbook. This is just a reinforcement. So if you still have any queries about this, we can just work out some more questions from the workbook or the progression test. Now I'm going to move into the third unit, which is describing motion, and this is the most fun part while describing motion, right? So when we describe motion, we use graph, right? From graph, we can tell about the motion of an object. If you remember over here in the previous unit, right? I described motion in these two tabulated forms, right? So I'm just going to go to this page and I'm going to use this idea that let's just say we have we have distance and time, right? I'm just going to make a rough graph to make you understand, right? If I'm covering 5 meters, 5 meters, and 5 meter, my distance is not changing, right? 2 seconds, 4 seconds, 6 seconds, and 8 seconds, right? So as you can see, the difference is 0 meters. So I'm not covering any distance because the interval is 0, right? So this, let's just say if I'm standing 5 meters away from you, right? So I'm not moving any farther or closer to you, but the time is constantly moving, right? The clock will keep on moving. So this is represented as a flat line over here, right? This is what we call as rest or stationary, right? Stationary means not moving, right? So this is the case of rest. I'm going to write rest so that you don't get confused by this word stationary, right? It's the same idea, just two different words. Now compared to this, I may be, right? Let's call this as A, B, C, and D, right? So this is A. So for B, I'm going to write D by T. I'm not going to write the whole things now, right? I'm just going to represent it as D or T. So this is 5 meters, 10 meters, 20 meters, oh sorry, 15, yeah, and then 20, right? 15 meters, then we have 20 meters, right? So 2 seconds, 2 seconds, 2 seconds, and 2 seconds. So for every 5 meters, I'm going to mark these as 5 meters, right? So I'm just going to be noting it till this, right? So every 5 meters or the equal intervals of distance and equal intervals of time. As you can see, this is one interval, this is going to be the other interval of distance, and the third interval of distance, right? And same way we're also covering equal intervals of time, right? So as you can see, when these bars on both sides are equal and these are also equal, we call this as uniform motion or constant motion, right? The same word, again, two different words, same thing, right? Uniform means something that does not change, constant means that does not change, right? So this is B. But in case of C, we have D by T, right? And as you can see, the graph is telling you that for equal intervals of distance, I'm just going to mark 1, 2, 3, and 4 points, right? Same way, I'm going to mark 1, 2, 3, and 4. If I'm just going to protrude time, right? So we have equal intervals of time. We've broken time into 4 equal parts, right? Compared to that, if you look at the distance, uh, you know, for the first, sorry, I'm just going to remove these, right? As you can see, the distance is slowly becoming larger, right? So over here, the difference is little, and the last one is a little larger, right? So this can be tabulated as, like, let's say 5 meters, 7 meters, right? uh, 11 meters, and then we can say 20 meters, right? So every 2 seconds, now the distance is changing very drastically. So over here we have a difference of 2 meters, over here we have a difference of 4 meters, over here we have a difference of 9 meters, right? This is visible over here, that the graph will try to bend towards the distance axis, right? So whenever the graph is closer to distance axis, we're going faster, and if it's moving away from the distance axis, then we're getting slower, right? And that's what case D is all about, right? So in case D, the values are going to be a little bit different, right? So we have D by T. This is part D, right? So we have, let's just say 5 meters, uh, we get 10 meters, then we get 14 meters, and finally we get to 17 meters. So this difference is 5 meters, right? I covered 5 meters in first 2 seconds, right? In the next two, I'm covering only 4 meters, and in the next I'm covering 3 meters. So I'm slowing down a little bit, right? So here we have speed being decreased, right? I'm covering lesser distance. I'm still moving forward, but I'm covering lesser distance every 2 seconds, right? And compared to this, in which the distance was increasing, the difference, right? The interval of distance was increasing over time. But remember, the interval of time must be same for the calculations to work out, right? So these are ways to represent graphs, right? So over here, I'm going to signify these some of these graphs. Let me just zoom in a little bit, right? Okay, so that you have a better understanding. Now over here, if you look, that this is a uniform speed. Why? Because it's a straight line. Whenever there's a straight line, we have uniform speed. This is distance, this is time. Over here, time is independent, right? Because our calculations do not really depend on time. It more importantly depends on distance. So we call this as dependent variable, right? A variable that is changing over this course of time, right? So the clock is not going to vary, right? The clock is not going to change. It will continue to count in seconds, but the distance will change depending on how fast or how slow I'm going, right? So if I want to represent this idea of motion in terms of graph, then if there's a straight line, right? Let's call this as from O. Let's call this point as A. Let's call this point as B, C, and then D, right? So from O to A, there's uniform speed. Now from A to B, as you can translate the distance, that the value of the distance is neither going up nor going down for AB. So we can say from point A to point B, the clock went on, right? This is the value for distance for AB, right? A and B. But over here, we have AB at the same point, right? The distance is not changing, so the object is not moving anywhere, right? Only the clock is moving. So this is stationary, or what we call as rest, right? So the object is resting, or it stopped, right? And then again it started moving faster. So as you can see, the angle over here is now a lot more, right, compared to the axis. So when the angle goes away, or as I said, if it moves towards the distance axis, we have increased speed or faster speed. And over here you can now see that the object is now moving or reducing the distance, right? Over time you can simply trace these points, any point, back to distance, right? And then you can see that this point, this point, this point, the distance is actually coming from here to here and then back to 0. So that means the object came back to its original position, right? Now let's do a practice question over here to help you understand better what is happening. Let's say there's a girl that wants to drop an object, right, and gets back home. So she starts walking at 9, right? She's moving towards the postal point. Let's call this point, right? So from this point to this, from let's O to A, and then B, then C, and then D. So from O to A, she's having constant speed, right? and the gradient is the angle or the steepness of this curve, right? This line, how steep it is. Steep means how closer it is to the y-axis, right? This is the y-axis and this is the x-axis, right? Okay. uh, from A to B she stopped for something, perhaps, right, to meet someone, and then she looked at the watch that she's getting late for her dropout, so she's going to run faster or ride faster, right? And then at that point, this is again constant speed but faster. Let's call this slow, right, compared to this one BC, right? And then from C to D she's returning again, that is constant speed, except that's returned to the start, right? She's coming back home. So now if we want to calculate, let's calculate speeds for each of these, right? For OA, speed is going to be distance over time, d over t. That is going to be, now just I'm going to reduce the size of the pen, right? I'm going to let's take this one, colorful one, right? So that we have a much better understanding what is happening. So I'm just going to translate this initial point. So initial distance, we're going to take the interval of distance and the interval of time. Since we are sure that she's having a constant speed, so we're just going to translate it. So it's 30, right? And from 0 to 30, right? So it is going to be 30 minus 0, which is the difference interval, right? And the intervals of time. So this is at 11 a.m. and 9 a.m., right? So that is from 11 to 9, it makes it 2 hours, right? So I'm just going to write the solution now. This is going to be 30 kilometers, and how much time she took? 2 hours, right? And these are not standard units, right? Standard unit is meters per second. This is not a standard unit, right? Keep that in mind. So her speed is 15 kilometers per hour, right? So each hour she's able to cover 15 kilometers. So hence she's able to cover in 2 hours a total of 30 kilometers, right? Now moving on from A to B, right? From A to B speed, right? Although she stopped, but we still have to prove it mathematically. So d by t, as you can see, for point A and for point B, the distance can only be translated to 30. That is going to be 30 minus 30, right? Which will give you 0 as an answer, right? So she's covering 0 kilometers in how much time? But the clock is still moving. So we have 1 hour, right? So over the course of 1 hour, she stops somewhere, right? And her speed is going to be 0 kilometers per hour because she's not moving, right? Now for B and C, as you can see, it's steeper. Let's calculate this, right? It is going to be B, the value for B is 30 and the value for C is 60, right? So the difference is going to be for BC speed is going to be d by t, which is going to be the interval, right? What is interval? The higher value minus the lower value. That is going to be 60 minus 30 gives you 30 kilometers, right? So the distance is 30 kilometers. And how much time she has taken? As you can see, she went from 12 to 12:30 because it's the middle of 12 and 13, which makes it 1 p.m. and 12 a.m. 12 p.m. and 1 p.m. So that is just 30 minutes, right? So 30 minutes, or what we can say, 0.5 hours, right? Since we are doing kilometers per hour, we need to keep the unit as the same for all to compare, right? I cannot just compete this over minutes. It would be wrong because I need to make the units right, right? Uh, so 30 divided by this makes it 60 kilometers per hour. So she actually went quite fast over here compared to OA, right? Because she's covering 30 kilometers in half an hour. So that means she can do 60 kilometers in 1 hour. If she can cover 30 kilometers in half hour, then she can cover 60 kilometers, double of that, in 1 hour because the time is doubled, right? So over here, r is considered as 1, right? And the distance is given as normal, right? For the final one, since it's a negative gradient, again, I told you from the final value to the initial value, right? So we're going to see a return. So it is going to be 0 minus 60. So what is the total distance for CD speed? It is going to be d by t. That is going to be 60 kilometers of total distance covered in how much amount of time? From 12:30 to 2 p.m., right? So that makes it 1.5 hours, right? 1.5 hours. So let me just pull up my calculator, right? I mean, so this is 60 divided by 1.5, right? So makes it 40. So that is going to be 40 kilometers per hour. That is return speed, right? How fast she came back home, right? Got it? So I hope you people are not able to understand the difference between sorry, just a minute. Able to understand what speed, how to calculate speed. Now there are more questions in your workbook. We are going through those questions, right? We recently did those questions. Now I want you to go through those questions again after reviewing this video, and if you still have any queries, you could come back to me in class, or you can leave any comments here and I can help you with that, right? Now moving into the last topic of this part 1, which is a turning effect of a force, right? So how a force can help you turn objects, right? So over here I'm going to use this example of a seesaw, right? If there's this, this assembly is there, right? We have a seesaw, right? We have this point is called the pivot, where this rod is balanced, right? And these are weight, right? Or you can say object, right? Object of a mass, right? Mass m, right? Whatever the mass is, right? So if this is object A and object B, if both A and B are going to be equal, and if the rod is balanced in the center, right? So this is going to be balanced, right? Because this downward force and this downward force are going to cancel the effect of each other. So this seesaw is not going to spin about anywhere. But let's just say if A and B are equal, then we have no rotation, right? This will not move, right? And this can only rotate because it's pivoted here. It cannot move linearly, right? It can only spin out, right? Now if A is greater than B, right? If A is greater than B, then definitely this way it will fall. So it will rotate this side, right, towards this side. So we call this as anti-clockwise. Now why we use clock as a counter of direction? Because we do know clocks move in one way, right? Which we call as the clockwise moment, right? So clock, as you can see, moves from 1 to 6 and 6 to 12, right? So that's clockwise movement. The reverse of that is called anti-clockwise movement, right? So if A is greater than B, then we're going to have anti-clockwise movement. And if B is greater than A, then we're going to see clockwise movement, right? Now I'm using the word movement while I'm writing the word over here moment, right? These are two different things. Do not confuse moment with movement, right? What is moment now? Moment is the ability of a force, of a linear force, right? Of a force applied in line, because forces are linear, which helps you turn objects or rotate objects, right? Let's have an example of this spanner, right? We're trying to open up a nut or screw, right? We do know that the screw is not supposed to, run around. It just rotates, right? It's fixed on an axis. So this pivot is called axis. Sorry, that is also pivot is the point where this object is supposed to rotate, also known as axis of rotation, right? Where this object is going to rotate. Now I discussed types of motion in the class, that there are several types of motion in which rotation is different from circular motion, right? In circular motion, the object is not fixed. Over here, as you can see, this bolt or this nut is going to be fixed in a way that it can only spin about this pivot, right? So it can only spin. So if we put a spanner to it and apply force, then we are going to have a rotation in this object. The same can be done when you try to unscrew a cap, right, of a bottle, right? Let's just say if you have a bottle, right, and you have a cap for it, so the cap is also screwed out, right? As you can see, there are threads over there, right? There are threads inside the cap as well. So you have to unscrew it, right, by rotating it, by spinning it. So for this case, you're applying force, right, with your fingers while the object is simply spinning. And over here, the axis of rotation is the center of the bottle, right? That's where the center is going to be. So the cap is going to rotate about that center, right? So this is what we call as moment, this rotational effect, right? So what is moment? I'm going to define moment now. Now please understand, this is not movement. Movement is motion, right? So moment, moment, or torque. There are two names for this. I prefer the word torque, but Cambridge uses the word moment, so I advise you to use the word moment, right? So what is moment? The rotational effect of a force. That's what we call as a moment. And that rotational effect depends on two things, right? That's a very simple idea. If you're supposed to open the lug nuts of a car wheel, then you see that there are very small spanners available with the car. But when you see someone opening up the lug nuts of a truck wheel, then you see they use very large spanners, right? And why the large? Because the farther you move away from this pivot point, the moment increases, right? If you're closer to the pivot, right, this distance d, let's call it d, let's call this as f, and let's call this moment as tau. And please don't mind, I love to write these Greek notations, right, because they're the ones who devised all these ideas, right? Newton and all those. So these units are there. So moment is represented by this symbol called tau, right? It's pronounced as tau, T-A-U, tau, right? It's a symbol. Just like speed is represented by V, distance is represented by D, and time is represented by T. We have this symbol tau for a moment or torque, right? In your book, they're just going to write the word moment. I'm using this symbol as well for my sake of ease, right? So over here we understand that this tau is actually the product of force into distance, right? How much force is applied and how farther that force was from this pivot, right? I'm going to put a cross over here, right, to represent that this is the center of or the axis of rotation, right? So the greater the force, the greater the moment. Let me just write moment, right? Because you guys are going to copy me, right? Eventually. So let's call this moment. So moment is force multiplied by distance. I'm going to write the word equation, right? Force into distance. Now remember, this thing is called word equation, right? Or simply equation. Why this is called an equation? Because there's this is equal sign over here, right? That's why we call this an equation in mathematics. So this is a mathematical representation of this rotational effect of the force, right? So it is very easier to understand. Let's just say I give you an idea. You have a big boulder that you want to lift. So how you're going to pull it up? You want to lift it up, right? Let's say it's 100 kilograms. So obviously I'm not able to lift it up. I don't know about you, but it's very heavy for me to lift up. I'm pretty sure you won't be able to lift it up with your hands just like me. So what we do to lift it up, we're going to use a lever, right? If you remember, we use levers to lift objects. We apply force here, right? And this force is going to create a rotational effect which is eventually going to lift this object up. Now remember, what really matters is how far the object is, right? Let's call it d2, second distance, and how far the force was applied, which is d1, right? So remember, these two forces need to be equal so that this can be lifted up. If this force is less then the average, the combination of these two, then definitely we won't be able to lift up, right? So we can simply use a longer lever to lift it up, or we can increase the amount of force. There are two ways to lift this object: increase the force or increase the distance, right? Right, we can use probably maybe let me use pink color, right? A longer one, right, to increase the force. As we see over here from this idea, that stronger moment is generated when the same force is at a larger distance, right? Either we increase the force or we increase the distance of the same force to increase the moment, right? Now over here, I'm going to give you an idea about how to balance how this distance work, right? So we're going to solve a problem. Let's just say I have this balance over here, right? Now remember, weight is a force due to motion, right? Over here we have 1 kilogram, right? And over here we have another weight. I want you to put 2 kilograms in a way that this stays balanced. You need to put it somewhere here. But where are you going to place it, right? If you place it at the end, right, over here, right? If you place it at this place, then obviously 2 kilograms is heavier, so we're going to see rotation in this side, right? We don't want that. So what we're going to do, how we can balance this, we are going to get a little closer to the center right here, so that the rotational effect from this force and the rotational effect due to this mass, they are equalized, right? They are balanced out to each other. This is what we call as balanced moment, right? Just like forces which are balanced and unbalanced, we have balanced moments and unbalanced moments. So I'll give you an example. What is a balanced moment? Let's just say if you have something, you have same masses at equal distance, equal masses, equal forces, right? If you remember, uh, equal forces and equal distance, right? That is what we call as balanced moment, right? That will yield a balanced moment. And if we have either uh, unequal, sorry, it's a little too long, right? Let me just have the same length. Okay. Compared to this is larger, this is smaller. So unbalanced moment. So we have either uh, unequal forces over equal distances, right? As you can see, this is 1 kilogram and this is 0.5 kilogram, right? Half. Or the other case, which is going to be like uh, 1 kilogram and then 1 kilogram, right? So equal forces over unequal distances, right? And definitely we're going to have rotation over here, same way over here, right? Anti-clockwise. So when the forces are equal, let's say the masses are equal, but they're not at equal distances. As you can see, this distance is small and this distance is a little bit larger, so we're going to have more effect, rotational effect of the force on this side. So this is how unbalanced moment can be generated, right? Or unbalanced case of forces, right? Although I've called it moment, I should rephrase this now properly as unbalanced forces causing moment, right? Okay, over here, balanced moment. I'm going to rephrase this now again as uh, balanced forces prevent moment, right? So they prevent the rotational effect of the force, right? Let's say this is 1 kilogram and this is also 1 kilogram, right? I hope I'm able to give you some of the basic ideas of how this all works out, right? If you still have any queries, do let me know. This is part one of this unit. I will upload the part two once we have covered those topics of workbooks in the classroom, as well as the topics, and had some discussion as well as the lab activities. I will update you soon enough. Thank you for your time. Bye bye.